In the last lesson, we learned about impulse and momentum. Momentum was how hard it was to stop an object. Impulse was the boost that we gave to an object. I'd now like to look at momentum and impulse in a collision involving two objects. So our first object will be approaching the second object from the left, and you'll notice when the objects collide, object 1 stops and object 2 starts moving. It turns out that in every collision, the total momentum before the interaction will equal the total momentum after the interaction. In this example, all of the momentum of object 1 was transferred into object 2, but the total momentum remained constant. We can also have a situation where the objects collide, and maybe this time the objects are sticky, so they stick together. They now move off together, but their speed is going to be half of the original speed. Their mass will be double the original mass, and they'll still have the same momentum that was present before the collision. So the big idea is that total momentum does not change during a collision. When you're trying to work out problems with total momentum, make sure when you account for momentum that you treat it as a vector. So in this case, object 1 will have a positive momentum, object 2 will have a negative momentum. When they collide, they stop, and it seems like momentum has been lost, but in fact it hasn't. The positive momentum of object 1 canceled with the negative momentum of object 2, and we had a total momentum of 0 both before and after the collision. This time we're going to have more momentum to the right than to the left, so afterwards the two objects will move off to the right. Again, we can affect the momentum by changing the mass of an object or by changing the velocity of an object. Again, the major idea behind momentum conservation is that during a collision, the total momentum before the collision has to equal the total momentum after the collision. So your equation looks like mass 1 times velocity 1 plus mass 2 velocity 2. That is all before the collision. Immediately after the collision, you have m1 v1 final plus m2 v2 final. They're the values immediately following the collision. It's best if you make yourself a little chart where you track object 1 and object 2. You need to know the mass of each object, the velocity of each object before the collision, and the velocity of each object after the collision. Now you can have one unknown value, and then you can use the equation to solve for that unknown. Let's look at a real collision between Allison Terrell and Brooke Phillips. Brooke was originally at rest and Allison was moving from the right. Okay, in this problem, Allison is approaching Brooke at a speed of 0.75 meters per second from the right. Brooke is at rest. You'll notice that after the collision, Allison came to rest. We want to know what speed will Brooke have after the collision. Okay, so we use the formula for momentum conservation. We plug in the values from above, and we find that Brooke will have a speed of 0.688 meters per second. The negative indicates that she's moving to the left, Allison's original direction. Now let's see a collision between Ashley and Jesse. In this collision, Ashley runs at top speed toward Jesse, who is at rest. Ashley has a mass of 65 and a speed of 4.5 meters per second. After the collision, Ashley continues to move forward with the speed of 0.5 meters per second. We'd like to find Jesse's speed post-collision. We use our equation for momentum conservation, plugging in the appropriate values, and we get a speed of Jesse of 4.33 meters per second.